All right, so today we get right into it. The derivative, which is the main idea of this whole course, differential calculus. We're going to unpack it today through the few lenses we've already explored, and then come to a formal definition, and then work through a few examples. So, what you've already worked through earlier in the course, we talked about the tangent and velocity problem. We call the tangent line the line going through the point a f of a that's parallel to the function f of x. That's the tangent line, right? It just kisses it once. It has the slope m given by this here, where we let the secant line slope approach the tangent line, right? We take x and let it get closer and closer to some a's value. So if this is the point I care about, A, I've got a curve doing something like this. So this is the point A and then f of A that I care about. And what we do is we take some point out here, we'll call it x, and let x approach A, and really it comes from both sides, but just for this picture I'll draw it from one angle. And we're looking at initially the slope of the secant line, right, which touches through 2 points. But as we let x come closer and closer, right, this point comes in, and we get instead the limit of this process, which would be the slope of the tangent line, right, which is usually a good bit off from what the secant line would look like, because it's only taking into account the slope at that one single point that we care about, x equals a. So this might be a moment, it might be a value that we care about, whether it be a cost or a distance. But this is the tangent problem. It was, how do we find the slope right at a single point? And so for a quick example to kind of refresh us, again, this is a purely geometric problem here, meaning we're not really talking about any physical quantities. This is just curves in the plane. So we'd say, all right, find the equation of the tangent line to the function f of x equals 3x squared at the point 1, 3. You'll need, so to get a tangent line equation, this is a common problem that we come up against. Remember, it's a line, so you just need the slope and a point in order to find the equation of a line. This could be y equal, remember you can use y equals mx plus b as an equation of a line, or you can use point slope form, which is y minus y1 equals m times x minus x1. M is always your slope. Well, it's usually your slope. And in this case, it's the slope of the tangent line. Tangent line slope. And this is how we find that particular slope, by taking the limits of the slopes of the secant lines as x approaches 1. So we take the limit as x approaches 1 of f of x, which we know is just 3x squared, minus f of 1. Well, f of 1 is just 3 times 1 squared, which is 3, all over x minus 1. This is the limit as x approaches 1 of 3x squared minus 3. If you'll notice, I can factor out a 3 up top, and then use again this property of limits to get around this removable discontinuity. Right here, this x minus 1 is a problem because I'm letting x shrink to nothing, right? This is kind of the inherent paradox in the problem. But since I can factor this out, this is in fact removable, since we're never actually going to x equals 1. And so this is really the same as the limit as x approaches 1 of 3x plus 1. And since this is a continuous function, I can just plug this in and say this is the same as 3 times 2, which is 6. All right, got cut off at the bottom there. But so this is what? This is the slope of the tangent line, right? So then if I'm looking for the equation of the tangent line, I know that this is, right, y minus y1 equals m times x minus x1. My slope is 6. The x value at this point is 1, and the y value at this point is 3. And so here we've got the equation of the tangent line. So typically when we're doing this, finding the slope is the hardest part because you're going to need to take the limit or find the derivative in some way. All right, the other part of this problem is finding just the point that it goes through, and that's usually given or easy enough to find. Okay, so this is the idea of the tangent line. Okay, finding something that's perfectly parallel to a curve at a single point. Something that took us thousands of years to come up with, by the way. So what we do is we kind of morph this definition of taking the limit of the slopes of the secant lines and not morphing it so much, but we're just saying, all right, instead of letting x go to a, let's instead talk about how x can move from a plus some tiny distance away. We'll call it h, which is that little shrink wrapper we looked at with time in the velocity problem. And what we get is an equivalent limit as is the limit as h goes to 0 of f of a plus h minus f of a all over h. Now, if you just let x equal a plus h in this limit and substitute it into here, you'll see that this is actually the same thing. So, if we were to draw it out, again, a similar situation arises. Here's some x equals a. Instead of saying some x distance away, we'll say it's some distance away h, which would mean that any point out here would be a plus h. And now you can see if I'm letting h go to 0, that means we're really letting this point come in, and we're moving from the secant line to the tangent line yet again. This more closely aligns with our definition of instantaneous velocity, where instead of x, we were talking about time t equals a, but it worked out to be the same exact limit, right? We're trying to shrink down that time window around that point so that we can find the instantaneous velocity at that single moment instead of the average velocity. So the key idea of the derivative is that it is the abstraction of both of these ideas, of the tangent line slope and the instantaneous velocity. And it really comes in 3 flavors, which I'll unpack in a moment. We call it the instantaneous rate of change, or the IROC, or the slope of tangency for any function f of x, as long as it's nice, right? It's smooth and continuous. We use this as the definition of the derivative of f of x at x equals a. That's what we'd call this. Now, what are the 3 interpretations? Because mathematics is abstract. It's general. That's what makes it so powerful. It sits outside of context a lot of the time. So the 3 interpretations are that it is the slope of the tangent line, right? So it is the line that just, the slope of the line that just kisses the curve. It's parallel at that singular point. It's also the instantaneous rate of change, which can be velocity, but it doesn't have to just be motion. And we can also call it like the sensitivity or the marginal change. I'll use delta here for the symbol for change. And we'll go through an example of what that really means. But it can really be broken into kind of 2 groups. The geometric understanding of what the derivative is, as well as the physical. I'll put this in quotes because I mean physical or contextual. It doesn't need to involve physics. It could be economics or biology. But I mean, kind of like an application more than a purely geometric problem like trying to find, the point of tangency on a circle, which is something that, Archimedes and his contemporaries were interested in. But usually nowadays we're more interested in the contextual physical applications of the derivative. But at any given moment in any given problem, you really need to kind of have all of these versions of it in your head since it's abstract. Okay, so here's a picture from the text, which is a little bit better than I can whip off on the sketchpad here. So the average rate of change is the slope of the line between P and Q. So that's this blue line here. The curve is f of x right here, this black one. So you can see how delta y over delta x, that's the slope of the secant line. And as we shrink that distance from x1 down to, or from x2 down to x1, what you'll start to approach, this q gets closer and closer, and so this line starts to tilt up and become the slope of the tangent line when we finally get infinitely close to that point. Okay. And so this becomes, at this point, the instantaneous rate of change when you measure this slope here, which is going to be different than over here. But the idea is that we can write this in a slightly different way, as long as we're comfortable with this idea of delta y being the change in y and delta x being the change in x. We can say that the derivative, which we use this notation f prime, the derivative is really the limit as delta x goes to 0 of the change in y over the change in x. This is equivalent to the other definitions we had up here. But what this allows us to do is see in the physical context a little bit more about the units. Because y will typically carry units and x will typically carry units. And if this is a rate or a ratio of differences, then it's going to carry the units of both the numerator and the denominator in a rate form. Okay, so again, you've already been exposed to these types of problems a few different times, numerically, graphically, exploring limits. But here I want to focus on these physical interpretations for a little bit because I find that this is where students struggle the most, is putting it down into kind of real world problems. So let's say we've got this function h, and h, all right, sorry about that. There's a 3-year-old with feet that weigh 1,000 tons, apparently. So he's making a lot of racket. So the function that we're looking at here in a physical context is h of t. It's the temperature in, let's say, Long Lake, New York at time t. Why? Because Long Lake is a beautiful place. And where t is the hours in a day between 0 and 24. Okay, so we got this function that's telling you that the temperature in time t is a continuous function. There's no breaks in it. Time is continuous. The temperature is continuous. So a couple of things to kind of render the function notation into English. What is h of 12? H of 12 is what? It's the temperature in Long Lake, New York at 12 o'clock p.m. Do we know what this temperature is? We do not. We just know what this notation would mean. So if we had an output for this, let's say we had it's 74, we would know that that means it's 74 degrees in Long Lake right now. Okay. Now, how about h prime of 12? Well, this prime notation tells us that we're talking about the derivative. What is the derivative? Great question. The derivative has 3 interpretations. It's the slope of the tangent line, it's the instantaneous rate of change, or it's the sensitivity or marginal change. Here, it would make the most sense in this physical context of temperature and time to talk about the instantaneous rate of change. Okay, so marginality doesn't really play here, and we'll do an example of where it does. So h prime of 12 really means the instantaneous rate of change. Now, the biggest problem I have with students struggling with problems like this, interpretation, is we'll use this word instantaneous rate of change, and that in itself is too general, right? This is an abstract idea. This is not telling this person next to you, maybe, who you're explaining this to, your coworker. It's not telling them in context what's happening. So it is the instantaneous rate of change. However, we can be more specific. What it means, if we unpack the notation, it's the limit as delta t goes to 0 of delta h over delta t. This carries the units of what? Degrees Fahrenheit over hours. This here will tell you a lot about the problem just looking at the units. Degrees per hour, right? So this is telling you the rate of change in degrees per hour, but we have to note the particular moment in time because this is changing throughout the day, right? It's changing at a different rate in the morning, at noon, and at night. So h prime of 12 really means the change in temperature per hour at 12 o'clock in Long Lake. Now, that's okay. It's more of a way to illustrate it here to you as a teacher to student, but what's really happening in terms of like a conversational way to interpret this. We typically don't say the change in temperature per hour at 12. We'd say how fast the temperature is changing, right? At 12 o'clock in Long Lake. That's what this means. And it has the units of degrees Fahrenheit per hour. Do we know what h prime of 12 is? No. But if we had a value for it, saying, let's say, let's pretend h prime of 12 was 2, that means that at noon, the temperature is changing at 2 degrees per hour. Now, this last part is h prime of 12 positive, negative, or 0? What do we think? What would we expect? Well, if it's noon, right, we have yet to reach kind of peak temperature throughout the day. That usually happens later in the afternoon. So what does this mean? It means the temperature should still be increasing, right? So what does the sign of h prime tell us about temperature increasing or decreasing? Well, if the slope of the tangent line is positive, that means we're increasing. If the slope of the tangent line is negative, that means we're decreasing. If the slope of the tangent line is 0, that means we're flat. So it would make the most sense that the temperature here would be increasing. It can obviously change depending on weather patterns and whatnot. But here we would probably expect that temperature would be increasing. Therefore, we'd expect a positive sign on the derivative. So those are a couple things you're going to want to pair in your mind, that a positive derivative means the function's increasing. A negative derivative means the function's decreasing. We can even add that in here. So for some function in general, f prime being positive implies that f of x is increasing at this point, right? It doesn't mean it's the case everywhere. It just means at the value that you're talking about. F prime being negative means that f of x is decreasing. and f of x equals 0 implies that f is flat. No change, right? If you've got no change, you're not going up or down. So graphically, a way to kind of show this, here we've got an increasing function. Here we've got a decreasing function. Oops. Here we've got a decreasing function, maybe. And here we've got a flat function. Right? This slope would be positive on a function here. This slope would be negative, rise over run, right? And here, this function has no change between 2 points. So it's flat. So this is a good thing to just kind of memorize. You need to understand why it's the case, more importantly, but it's also just a good thing to drill into our brains. What a pleasant visual. And so this is a physical interpretation of the different notations that we'll see. H prime, I'll introduce you to another notation in a later video. And then again, the sign of the derivative and what that means. So this is the instantaneous rate of change in the physical context. One more problem I wanted to show you was on interpreting something as a marginal change or sensitivity. Okay, so this can also be a bit confusing, so I wanted to do a specific example. So let A of t be the daily cost in dollars of air conditioning the interior of FLCC when it is T degrees Fahrenheit outside. This is often called the ambient temperature, right? Because it is what is surrounding the school, okay? So let's start here with interpreting this function notation again. What is A of 80? A of 80, well, we input 80. The input is degrees. The output is cost. So A of 80 is the cost daily in dollars of AC when it is 80 degrees outside. All right, so that's pre-calc stuff. What is the meaning of A prime of 80? All right, well, again, this is really the limit, as we could say, as delta t approaches 0 of delta A over delta t. And again, these units are going to be what? Dollars per degree Fahrenheit. And so again, here a kind of lackluster interpretation would be to say, oh, it's the instantaneous rate of change of the temperature, of the cost as temperature increases. And that's not wrong, but it also just doesn't really help as much as we could get into the nitty gritty of it. So here, since we're talking about the cost and the temperature increasing is somewhat continuous, but it's a bit unpredictable. It's not like time. So typically how we would render this into speech is we'd say this is the change in daily cost per degree increase. So this is what we mean by marginal change, because we're talking about per 1 degree increase. So oftentimes if it's not a clear rate like miles per hour or something like this, we might be looking at a marginal rate of change. So where we assume that we have a unit rate in the denominator. So for example, if we said A prime of 80 was like, let's say it was 2,500. Okay, what would this mean? This would mean that it would cost $2,500 to cool the building if the temperature increased from 80 to 81 degrees Fahrenheit. This would be a solid interpretation of what this means. Okay. So it's the cost to cool, it's the change in the output based on if we increased the input by 1. So you can see how this would be a little bit more helpful than to say, oh, it's the instantaneous rate of change of the cost with respect to temperature, right? That doesn't really help so much. But if we're, the maintenance crew or the head of grounds and we see, oh, well, this tells me that, we got to be budgeting for this, assuming, the temperature, whatever it might be. This is just a more informative way to interpret this notation. Okay, so what are the units? As we said already, it's going to be dollars per degree Fahrenheit. And what would we expect for the sign? Right? Is it going to be positive, negative, or 0? Well, here I kind of gave us an example that might give it away. But if this is the ambient temperature outside, right, and we know that more cooling costs more money, right? If the temperature went from 80 to 81, which as we do along our x-axis, if it went from 80 to 81, we'd expect the cost to go up because we have to cool it down further, right? So it would make sense that a prime of 80 is greater than 0 because it would cost more if the ambient temperature outside increased to keep it cool, right? To stop it from, to stop the inside from getting to that ambient temperature. Okay, so this is an example of the one way that we can interpret the derivative, which sometimes we call it sensitivity, sometimes we call it marginal change. It feels a little clunky, but it's once we realize that we can describe this as the change in the output for a change of 1 in the input, that it kind of opens up the way that we can talk about the instantaneous change. So the derivative, it's 3 interpretations. It's the limit of the slopes of the secant lines. It's the instantaneous velocity. It's the sensitivity or marginal change. It's all of these things and more. It's an abstract idea, and this will be, again, the fundamental concept for the rest of the course. So will you understand it completely now? No, but by the end of the course, you absolutely will, and we'll apply it on all different sorts of problem-solving situations so you can really see the power behind this idea. So, hope you found that helpful. We'll see you in the discussion, and enjoy.